Environment, health, safety, and semiconductor manufacturing. In the semiconductor industry, a strong focus on environment, health, and safety, commonly referred to as EHS, is critical to ensuring not just business performance, but also human and environmental well-being. This commitment centers on protecting people, the planet, and performance. Environmental responsibility includes implementing sustainable practices to reduce waste, conserve energy, and minimize chemical emissions. Clean rooms and advanced filtration systems are just one way to safeguard air quality and limit environmental impact. Health focuses on worker wellness, including ergonomics, chemical exposure prevention, mental health support, and routine health checks. Employees are the core of this industry, and their well-being drives operational success. Safety involves robust risk management systems, from emergency response planning to equipment safety protocols and hazard identification. Together, these pillars form the foundation of a responsible, high-tech manufacturing culture that prioritizes long-term sustainability and the protection of all stakeholders. EHS as a framework for responsible manufacturing. Environment, health, and safety. EHS is a comprehensive framework that supports responsible manufacturing in the semiconductor industry. It emphasizes the integrated management of environmental impact, worker health, and operational safety. From an environmental standpoint, EHS promotes waste reduction by minimizing hazardous materials and improving recycling processes. Resource conservation is achieved through optimized water and energy usage, while emission control reduces the release of harmful gases into the atmosphere. These efforts support long-term sustainability. On the health side, EHS focuses on exposure prevention, ensuring employees are not harmed by chemicals, radiation, or particulates. Health monitoring programs track vital signs and detect issues early. Occupational wellness promotes mental and physical health, while chemical safety protocols ensure safe handling and storage. Safety initiatives include accident prevention through training, risk assessment procedures to identify hazards, equipment safety measures, and strong regulatory compliance. Together, these elements form a powerful system for continuous improvement in high-tech environments. Integrated approach to EHS in semiconductor manufacturing. In semiconductor manufacturing, the environment, health, and safety framework operates as an integrated system. These three pillars work collaboratively to create a sustainable, healthy, and safe work environment while simultaneously supporting operational excellence. The environmental pillar focuses on reducing the industry's footprint, evidenced by a 70% waste reduction achieved through recycling initiatives and process optimization. The health pillar emphasizes compliance and monitoring, achieving a remarkable 99.8% rate in health compliance. This indicates that protocols for chemical safety, exposure prevention, and employee wellness are being effectively implemented. The safety pillar targets zero incidents through preventative measures, training, equipment safeguards, and risk assessments. By aligning sustainability with worker health and safety, this integrated approach ensures that responsible manufacturing practices are not only policy, but embedded into everyday operations. It reinforces the idea that protecting people and the planet enhances productivity, quality, and company reputation in the high-tech manufacturing sector. Key manufacturing steps in semiconductor production. Semiconductor manufacturing is the foundation of modern technology, powering everything from smartphones to supercomputers. The process begins with wafer preparation, where high-purity silicon is transformed into a flat, polished substrate. This silicon wafer serves as the base for all subsequent layers and structures. Next is lithography, where intricate patterns are created on the wafer using ultraviolet light and photoresist materials. These patterns define the circuitry for transistors and interconnects. The third step is etching, which removes selected areas of material to form precise features. It can involve dry or wet techniques depending on the process requirements. Deposition follows, in which materials are added layer by layer to build up device structures. This includes dielectric, metal, and semiconductor layers. Finally, testing ensures quality control by verifying that electrical parameters and physical dimensions meet specifications. Each step must be carefully controlled to ensure performance, reliability, and high yield across every chip produced. Why EHS is critical in semiconductor manufacturing. Semiconductor fabrication occurs in an ultra-clean environment to meet the extreme precision demands of the industry. Class 1 clean rooms maintain fewer than 1 particle per cubic foot of air. To achieve this, workers wear full-body protection, bunny suits, gloves, and masks to prevent contamination. HEPA filtration removes 99.97% of airborne particles, and the cleanroom's temperature, humidity, and pressure are tightly controlled. EHS is critical because over 500 chemicals are used throughout the process. These include toxic substances such as arsenic, lead, and various strong acids. Workers are also exposed to hazardous gases that may be flammable, corrosive, or chemically reactive. Additionally, energy sources like UV light, plasma, and high voltage introduce further risks. With 24/7 operations, over 300 process steps, and a target of 99.9% precision to achieve near-zero defects, maintaining strict environmental, health, and safety protocols is not optional. It is essential for protecting people, products, and processes. Managing environmental footprint in semiconductor manufacturing. Semiconductor fabs require significant energy and resources to operate, yet companies are working to manage their environmental impact through sustainable practices and responsible resource management. Each fab typically consumes between 2 to 4 megawatts of power, primarily driven by 24/7 operations, extensive cleanroom systems, process equipment, and cooling demands. This accounts for roughly 30% of city-level power usage. Water usage is also substantial, reaching 7 million gallons per day, which is necessary for cleaning, rinsing, and temperature regulation. More than 500 different chemicals, ranging from acids and solvents to metals, are used in processing steps. Effective chemical waste management is critical, with specialized treatment facilities and robust recycling and recovery programs in place. The industry goal is zero chemical waste sent to landfills. Finally, emission control systems are highly efficient, achieving up to 99.9% containment, contributing significantly to minimizing environmental emissions. Water, air, and sustainability efforts in semiconductor manufacturing. Managing the environmental footprint of semiconductor fabs requires efficient water usage and air emission control, supported by long-term sustainability initiatives. Water usage is optimized through ultra-pure water systems, essential for wafer cleaning, rinsing, and cooling tower operations. These facilities also include water reclamation systems that enable an impressive 95% of the water to be recycled. Air emissions are tightly controlled with advanced technologies that capture over 99% of volatile organic compounds, VOCs, particulates, and process gases. Scrubber systems and filters play a key role, and real-time monitoring ensures consistent compliance with environmental standards. Broader sustainability goals include a transition to 75% renewable energy use by 2030. The Circular Economy Initiative supports 85% material recovery, minimizing waste. Finally, companies are committing to carbon neutrality, with a goal of achieving net zero emissions by 2050 through strategic planning and investment. Worker health and chemical exposure risks in semiconductor manufacturing. Semiconductor manufacturing involves the use of over 500 different chemicals, including more than 50 known or suspected carcinogens, which presents significant health risks to workers. These risks are present around the clock due to 24/7 operations, making consistent exposure a serious concern. To mitigate these risks, 100% usage of personal protective equipment, PPE, is required for all personnel. Chemical hazards are classified as high risk due to the presence of toxic materials like arsenic, benzene, and formaldehyde, recognized carcinogens. Acids such as hydrofluoric, hydrochloric, and sulfuric acid can cause severe burns. Solvents may lead to skin and eye irritation, or even central nervous system effects. Heavy metals like lead and mercury are linked to neurological damage. There are also reproductive health concerns, supported by studies showing increased miscarriage rates. In response, companies have implemented monitoring programs, exposure control policies, and restricted access protocols for high-risk areas. Respiratory and physical hazards in semiconductor work environments. Semiconductor manufacturing presents a range of complex respiratory and physical hazards that require strict controls. Airborne contaminants are a major concern, including toxic gases like ammonia, silane, silicon hydride, and phosphine, which pose inhalation risks. Particulates such as silica and metal dusts are also prevalent, along with vapors from organic solvents and chemical vapor deposition precursor chemicals. Plasma processing can generate hazardous byproduct gases. Due to these airborne threats, 95% of workers in high-risk areas must wear respirators. Physical hazards are equally serious. Radiation exposure from UV lithography and ion implantation is common, along with electrical dangers from high voltage and radio frequency fields. Thermal risks arise from furnace operations and cryogenic materials. Ergonomic issues, such as repetitive motions and lifting, can cause long-term strain. Protection strategies include N95 and Me100 respirators, eye splash guards, chemical-resistant suits, continuous air monitoring, and routine medical surveillance for early risk detection. Workplace hazards and safety protocols in semiconductor facilities. Semiconductor manufacturing environments must address complex workplace hazards through strict and comprehensive safety protocols. Facilities operate with 480-volt electrical systems, presenting high-voltage risks that require specialized training and protection. Emergency readiness is critical. Operations run 24/7, and emergency plans must always be in place. Lockout, tagout, LODO procedures are enforced 100% of the time to ensure safe equipment maintenance. Additionally, cleanroom environments meet Class 1 standards, maintaining the highest level of air purity. Equipment hazards include moving robotics, high-pressure systems, crushing or pinch points, and exposure to hot surfaces such as furnaces. These present a high level of risk. Electrical safety measures include arc flash protection, ground fault systems, control of static discharge, and RF radiation mitigation. Confined spaces are another area of concern, requiring gas monitoring, proper ventilation, atmospheric testing, and formal rescue protocols. Access is strictly permitted only with proper training and documentation to ensure worker safety. Hazardous energy, emergency response, and ergonomic risks. To ensure full compliance and safety, managing hazardous energy is a top priority. Lockout, tagout, or LODO protocols are essential to prevent accidental energization of equipment. This includes energy isolation verification and enforcing multi-person procedures to ensure no single point of failure. Emergency shutoffs must also be clearly accessible and well marked to protect everyone in the facility. Emergency response readiness is another pillar of safety. A 24/7 crisis management framework covers chemical spill response, fire suppression systems, evacuation procedures, and medical emergency plans. Each scenario must be practiced through drills and supported by clear documentation and signage. Lastly, ergonomic risks must be addressed to reduce workplace injuries. Preventing musculoskeletal disorders involves strategies like minimizing repetitive strain injuries, implementing heavy lifting protocols, improving workstation design, and managing fatigue during extended shifts. These areas work in tandem to create a safer, more efficient workplace. Integrated Safety Management System. An integrated safety management system forms the backbone of a proactive safety culture. It starts with continuous risk assessment, identifying potential hazards before they escalate into incidents. This involves regular audits, inspections, and engagement with workers on the floor. Mandatory safety training ensures all personnel are certified and aware of the procedures and risks. Engineering plays a key role. incorporating safety by design principles directly into equipment and facility layouts. This helps minimize risk from the outset. Clear, standard operating procedures ensure consistency in safety practices across departments. Real-time safety monitoring provides oversight, allowing for rapid intervention when deviations are detected. And finally, continuous improvement ensures the system evolves. Lessons learned from audits, incidents, or feedback must be used to refine processes and elevate safety standards over time. Together, these components build a resilient, adaptive safety infrastructure that protects people, equipment, and operations. Regulatory compliance in semiconductor manufacturing. Navigating complex regulatory frameworks is essential for safe and legal operation in semiconductor manufacturing. More than 35 OSHA standards apply to workplace safety, and 100% compliance with these is non-negotiable. These standards govern a wide range of activities and hazards. The NESHAP guidelines, issued by the EPA, address hazardous air pollutants, while SEMI provides valuable industry-specific guidelines to align with best practices. Key OSHA standards include 1910.119, which governs process safety management, and 1910.134, which covers respiratory protection. Lockout-tagout protocols are enforced under 1910.1147, while 1910.1200 ensures proper hazard communication. For heavy metals, 1910.25 regulates exposure to lead and arsenic. EPA regulations complement OSHA by addressing environmental impacts. These include the Clean Air Act, RCRA for hazardous waste, TSCA for chemical substances, and EPCRA for public right to know. Together, these standards ensure protection of people, the environment, and organizational integrity. Industry and international standards. Compliance in semiconductor manufacturing extends beyond local regulations and must incorporate both industry-specific and global standards. SEMI standards are tailored for semiconductor environments. SEMI S2 offers environmental, health, and safety equipment guidelines. SEMI S8 addresses ergonomics engineering, promoting safer and more efficient workstation design. SEMI S10 introduces a formalized risk assessment process, helping identify and mitigate potential hazards. SEMI S21 emphasizes worker protection, while NFPA 318 outlines standards for protecting fab facilities from fire and other risks. On the international side, ISO standards guide global compliance. ISO 14001 focuses on environmental management, and ISO 45001 sets expectations for occupational health and safety. IFC Chapter 27 relates to fire code requirements specific to semiconductor facilities. Additionally, EU REACH handles chemical registration and safety, while RoHS restricts the use of hazardous substances. These frameworks ensure manufacturers meet both global and local safety, health, and environmental obligations. Integrated compliance management. Integrated compliance management ensures that all regulatory obligations are met through a structured and ongoing process. It begins with thorough assessment activities, including regulatory gap analysis, to identify where current operations fall short of requirements. Once gaps are found, documentation efforts are needed to establish clear policies and procedures tailored to each compliance area. Training ensures that every team member understands and follows these procedures, enabling a workforce that's not only informed but accountable. Continuous monitoring provides real-time insight into how well compliance is being maintained, while scheduled auditing helps verify conformance and drive corrective actions where needed. Updates play a vital role in keeping the system agile, especially as regulations evolve or new standards emerge. Together, these 6 elements — assessment, documentation, training, monitoring, auditing, and updates — form a closed-loop system designed to maintain full compliance and reduce risk in complex, highly regulated environments like semiconductor manufacturing. Driving safety excellence. Achieving safety excellence requires setting ambitious goals and aligning them with innovative practices and strong collaboration. A key metric is the total recordable incident rate, or TRIR, with a target of 0.2, indicating a high-performance, low-incident environment. A 100% safety culture is not just a goal, but a daily standard, where safety is embedded in every action and decision. TZE, or Toward Zero Exposure, is the philosophy of eliminating all possible hazards, no matter how small, to protect every individual. This is supported by a commitment to 24/7 continuous excellence, reinforcing that safety does not pause during breaks, shift changes, or downtime. This culture requires commitment at every level of the organization and focuses on proactive behaviors that prevent incidents before they occur. Success comes from uniting leadership, data insights, and process discipline to build a resilient and safe working environment. Safety culture and continuous improvement. A strong safety culture puts people first. It begins with leadership commitment, where management sets the tone and models safe behavior. Employee engagement and empowerment give individuals ownership over safety, encouraging them to speak up and take initiative. Open communication supports transparency, allowing safety concerns to be raised and addressed without fear. Behavior-based safety programs identify at-risk actions and reinforce safe choices through coaching and observation. Recognition systems celebrate individuals and teams that uphold safety values. Meanwhile, continuous improvement is the engine that sustains progress. It relies on data-driven decisions informed by analytics and thorough incident investigations that uncover root causes. Benchmarking compares performance against industry leaders, setting a standard to strive for. Regular audits and assessments ensure the system remains effective while lessons learned are documented and shared. This PDCA, plan, do, check, act, cycle of excellence helps prevent repeat issues and fuels long-term safety success. Innovation in tech and industry leadership. Smart Safety, or Safety 4.0, relies on next-generation solutions to elevate protection and performance. IoT sensors enable real-time monitoring of environmental and equipment conditions, detecting issues before they escalate. AI-powered risk prediction analyzes vast data to forecast hazards and recommend actions. Digital twins provide virtual models of systems for safety scenario testing, allowing predictive adjustments. Wearable technology monitors worker health and exposure, improving situational awareness and response times. Automated safety systems reduce the potential for human error by executing pre-programmed protective actions. Alongside these technologies, strong industry leadership sets the benchmark. Participation in the SEMI consortium ensures alignment with global semiconductor standards. The commitment to Toward Zero Exposure drives innovation in safety. Sustainability initiatives show leadership in environmental responsibility, while cross-industry collaboration promotes shared learning. Disseminating best practices builds a more resilient safety culture across the industry and positions organizations for excellence recognition and awards. World-class EHS excellence model. A world-class environmental, health, and safety EHS excellence model integrates 7 core pillars. It begins with a clear vision, zero harm aspiration, that sets the goal for safety outcomes. Leadership shows visible commitment by actively championing safety in decisions and behavior. Engagement ensures workers participate meaningfully in safety planning, reporting, and improvement. Systems integration ensures that all safety functions, risk management, compliance, training, and operations work in harmony. Metrics track performance, helping identify strengths and areas needing attention. Innovation emphasizes the proactive adoption of new technologies and methods to improve safety results. Finally, partnership with industry groups, suppliers, and regulatory bodies strengthens collaboration, enabling organizations to stay ahead of emerging risks and compliance changes. Together, these elements form a robust, adaptive model for EHS excellence that protects employees, supports productivity, and builds a sustainable safety culture that continuously evolves with the needs of a dynamic manufacturing environment.